in abstract. Basically, in abstract, you can see we are studying the least action principle. Least action principle basically tells a particle takes that path for which the action is minimum. Basically, it has been formulated. It was formulated by Meera and further by Hamiltonian for conservative system. But as we know, in our physical world, most of the physical systems are non-conservative, so it is needed to be formulated also for non-conservative or a dissipative system. Recent works have been done by Lin and Wang in around 2014 and currently by Ashwin Vedya in 2019 and 21. I have taken their reference as a base paper. They have studied the non-conservative system, which is simple pendulum. But I am studying a spring mass system for linearly and cubically damped plus forced oscillation. Here is the overview of the talk that I am going to discuss. Now coming to the introduction. Wants to know the nature's mind? Yeah. Nature follows the least action principle. First of all, come to know what you mean by least action principle. Least action principle means a particle takes the path for which the quantity called action or energy consumption is minimum. Not always, it is stationary actually. And it is what that path can be called as a true path or the optimal path. Now, how it can be obtained? It can be obtained by two ways. First, by our Euler-Lagrange equation, and thereafter by Newton's laws of motion. Now, as you can see here, the graph from Q2 represents the generalized coordinate position 1 and Q1 represents the another position. Particle is moving from here to there. As you can see, there is a faint red color and bold red color. Bold red color represents the path that actually particle takes, and these are the paths that can be possible because. Take a simple example. You are going from point A to point B. There are infinite possible ways that you can go through it. So actually, you can calculate the true trajectory of that particle by using the equations of motion. And the Euler-Lagrange equation of motion can be derived from the action. Here S is defined as the action, which is integration over 0 to L dt. And this is our famous Newton's equation, F equals to d p by dt and d square s by dt square. Now, moving further, some literature review. In history, basically, the systems are made for the conservative system. First by Meera in 1744. What does Meera's action principle tells? It tells basically the path followed by the physical system is one for which the length is minimum. What are the constraints or assumptions taken by him? The first is like fixed in point, like all the particles should move from point 1 to point 2, and the other, all the paths have the fixed in point. And other is a fixed energy. For every path, the energy should be fixed for a particle. Here, one important point should be noted that the energy conservation is an assumption, not a consequence. And the mathematical formalism is like S naught equals to integration P d Qi. Now, thereafter comes Hamiltonian. Hamiltonian gives his principle in 1834, and what he takes, he basically says that the dynamics of a physical system can be calculated using variational calculus by using Lagrangian, and he basically says the particle takes that path for which the action, which is the quantity defined as the integral L dt, is minimum. What are the constraints in his theory? In his theory, there are two constraints. First, there is a fixed in point, which is similar to the previous one, but the other constraint is fixed time interval. Like for the all paths, the time taken by the particles should be constant or the same. And the fourth, which is most important point, in his theory, basically energy conservation is consequence of the situation, not an assumption. Now, this is the mathematical formalism that you can see here. Now, what is the research gap? What we are talking about? What we are searching actually? Basically, you know, most of the physical system in our nature is non-conservative, but we don't have any single or like unified principle to deal with it. But now what? There are some proposals that are like saying that I have given some ideas to include dissipative system in the action principle, like done by Rayleigh dissipation function, Batman, fractional derivative, pseudo Hamiltonian mechanics. These are the terms. I don't know too much about this, but a little bit I know about this. But still have drawbacks. Now what? Here comes the proposal. Basically, first of all, I want to discuss a question for you. Let's suppose there is a ball projected at some angle horizontally in a deep space or a vacuum. You can calculate the trajectory by using Euler-Lagrange equation or by using Newton's laws of motion. And when we calculate the action for that path, it is coming to be optimal or like minimum action compared to the other path taken by the particle. But it is in deep space. If I ask you a simple or similar question to perform the same experiment, well and good. But if I ask you the same experiment to perform in air or friction, will now the path be the optimal one or having the minimum action or not? Our work is to search into this or to search out this whether the path taken by the particle in the dissipative environment is minimum having action or not. Now, Now you are like, okay, I don't know. Let's see. Then this is the hypothesis. Basically, drawbacks in the previous work, which I told as a Rayleigh Batman approaches, they have limited application to only some systems and friction. Like as you know, friction in the environment, dissipating environment basically depends on the velocity, power. So they only work for certain types of frictional forces. Another is the lack of energy connection with the Lagrangian. As you know, Lagrangian is the difference of kinetic energy minus potential energy. So they have the lack of energy connection. And the most important thing, they have the lack of optimal characteristics of the part taken by the particle. Now, what is the solution proposal? As I discussed, the proposal proposed by recently approached by Wang and co-workers in ITNA, like 2015, also studied by Ashwin Vedya 2019 with Kathleen Rhodes in 2021. What is his idea? He is basically taking the idea that he is constructing the Lagrangian for a system. Let's suppose there is a body which is moving in a dissipating system, but if you consider the body and the system, the environment and complete as a system, then the body is radiating energy to the energy is going from the body to the environment. But if you take whole as a system, the total energy should be conserved. He is taking this idea to formulate his action principles. As you can see here, that body plus environment have the total energy conserved. Now, theoretical and mathematical framework that I was using in my work, least action principle with dissipation is an open question in classical mechanics. When described the dissipating Lagrangian that accounts for the energy accelerated consisting of damped moving in its environment coupled by friction force. In this way, energy of the total system is conserved. This is the basic idea that he has taken, that a total system should have constant energy. Hamiltonian can be written as a K1 plus V1 plus ED. Here K1 is the kinetic energy of body, V1 is the potential of the body, ED is the amount of energy transferred from the body to the environment. You can write H1, Hamiltonian for body, K1 plus K2, and like H2 for K2 plus V2 plus ED. H2 is the Hamiltonian of the environment. K2 is the you will see here that certain assumptions have been taken. K2, like as the environment doesn't move, heat basically taken that the environment should not move, and also the environment is not interacting with each other. So V2 is also 0 and K2 is also 0. After taking these assumptions, your equation reduced to H is equals to K1 plus V1 plus ED, and you can calculate the Lagrangian by using Legendre transformation, which is basically PQ dot minus L. Or if you reverse the equation, minus H. So here our action principle, as I defined, integration T1 to T2 L dt. When you put the Lagrangian over here, and where ED can be you will know that the work or energy can be calculated by integration force into displacement, and this you can write displacement in the form of x dot dt. And when you move further, following equations can be derived. You can put all mathematics, it is in the paper, you can easily do. And this is our the desired equation that we want actually. And we can put the values in the last equation corresponding to define the model like a spring mass system, which I have taken. So in our equation we have like d square x by dt square, a is the damping coefficient, n is the damping power, plus omega square, f naught is the force oscillation with a coefficient. Now moving to the further, what I have studied, basically in the previous work have been done on a simple pendulum, and results are given and predicted, predictions are done. Now I am studying a different model, which is a spring mass system along with force oscillation. Keep in mind, by taking same approach by Wang, and I am calculating the results for a spring mass system, comparing my results for their prediction, will verify their method, where they will the method that they have used to solve the problem is actually correct or not. It is basically a quantitative approach. Thereafter we can go for the qualitative approach when we come to know, okay, the results are not matching. Here are the some results. As you can see in the left side, before I will tell you one thing. Basically, let's suppose a particle is moving from point A to point B. There are multiple possible paths that particle can take. We can calculate the actual path that particle can take by Newton's equation of motion, and we can also calculate the other part by using perturbation, which can be done by using polynomial approximation or using Taylor series a little bit. So after calculating all the trajectory, you can calculate action for particular trajectory and plot that for which path the action has a minimum value. Our work is to check the same thing for a dissipating system. As you can see here in the graph, for the simple pendulum case, as I have defined, n equals to damping power, t equals to time duration for the particle or body is in the damped environment, a is equals to basically your coefficient of damping. So as you can see here, this is the plot of action versus path. Here The red line shows the optimal action, which is lying below the all perturbated path. Means like all other paths have more action as compared to the optimal path. This conserves the optimality character of the least action principle. Same similar in a spring mass system, the same results is occurring. In the second case, if you change the parameter, you are looking at the both are getting closer. But in our case, it is almost like overlapping. So results are not too much matching. Moving forward and changing the parameters, you can see here also the optimal character is valid. In our case also there is variance because red line represents the optimal action and other blue stars are representing action corresponding to different path. Here it is like around 10 paths are such for which the optimal character has lost. And here in our case like 20 parts have lost the optimal character. And means like what I am saying, as we move to the dissipative system and change the parameter, the optimal characteristic is no longer valid till now. Here are some results that you can go through it. And now this is for only damped water. When we move to the force oscillation, the results are like we have lost the optimal characteristic in case of dissipative system. Now the results will be more important, important when we move to Hamiltonian. According to the theory, Hamiltonian represents the total energy and total energy should be conserved or constant. But when we move to the optimal case or force case, the Hamiltonian is no longer conserved. In the case of a spring mass system, even in the case of pendulum, they have not studied this. As you can see, Hamiltonian is changing with the time for various parameters of the result. These are the results for Hamiltonian, which is most important of my work. You can say that is not studied yet. Basically, this is the conclusion is Hamiltonian doesn't remain the constant for the force oscillation, and action is no longer minimum even for the linear damping case, and the loss of optimality character is more sensitive to time than damping coefficient. I still have a job to work. Means future work. You can verify aerotaken approach by considering different methods with force oscillation on comparing different results. We still have not satisfied physical experiment as a base to check our results, and qualitative approach can be done like in the above approach solved. There is a non-locality problem which we have to look even now. Here is the reference, and thank you. Thank you very much. Any suggestions?
The speaker spoke for 12 minutes and 26 seconds.
What is the non-locality problem?
Yeah, basically the non-locality problem is occurring that let's suppose there is a path. Particle takes from point A to point B. When we along the
in the mathematics where the non-locality is there.
Basically non-locality is occurring in the same this way. Let's suppose there is a point QA and there is a point QB. Particle is going from here. This is, let's say, the through path or through trajectory. When you put perturbation in a trajectory, like these are the perturbated paths, actually the non-locality is occurring in the case of ED. ED is the amount of energy transferred from the body to the environment. The expression for ED is like minus of integration, you can take x as t naught or x as a t, and here you can write x dot or d dot. Basically, when you write the action, for action there is an L dt. And when you write the Lagrangian, which is here k1 minus v1 minus ed, so you can easily see Lagrangian is calculated over let's suppose t equal to t1 to t equals to t2. When you move to t equals to t1, t2, in the case of ed, when you put Lagrangian over here, t1 to t2, like kinetic energy k1 minus v1 minus ed. In the case you can see in the case of ed, there is one more integration over there.
Okay, fine.
X dot yes.
Then this non-locality should manifest in the equation of motion also, or is it not there in the equation of motion?
So, basically what I want to say that equation of motion is not a concern of this topic. Because
there must be some equation of motion also.
yeah, there is a equation of motion.
What is that equation of motion? It's just linear damped harmonic oscillator or some.
No, it is both linear damped harmonic oscillator and cubic damped harmonic oscillator.
But is that equation of motion local or not local?
Equation of motion is local. But if I ask you, what about the action? What about the action, that is particle taking about the perturbated or different paths? What about the value of action? Will the optimal characteristics that previously people are talking?
But action is not local. Action depends on the entire trajectory.
But in the case of conservative system, when we study conservative system, there is not such thing like double integration. In which case, basically in the ED case.
But what is non-local? What are you saying is non-local?
I am saying the non-local.
Equation is local. Is the action
Your
local?
differential equation is local.
What is not? Is the action local or not?
No, action is not.
But the action is not local even in traditional MBE.
So it is local in traditional basically. It is local. Basically, it is local in this sense. First of all, I want to figure out what does I mean by non-local here. Basically, non-locality means that the particle and the true path of the particle is this. Let's suppose you are calculating Lagrangian at point this. So if you are calculating the Lagrangian at this point, the term ED, which is the effect of amount of energy dissipated from the system to the environment, the value of L over here is affected by the previous value because this is the non-locality acting in this paper.
So what?
So what? Because when you, so what is that? When you actually, you know, basically, by action, you can get to the Euler-Lagrange equation. But if you use this Lagrangian over here and do the traditional method, you would get to a wrong equation. So people means like when you go to the wrong equation, you can check the mathematics in his paper.
But then where does this action, then why do you want this action to be there? If this action gives you the wrong equation, which action gives you? The top one.
This Lagrangian. By using this Lagrangian, action gives you the wrong equation.
Then why are you calling it action?
Basically, what happens, like to solve this problem of dissipative system, many people have tried a lot of approaches, but there is lack of some. There is some drawbacks. One people are confused.
Is the equation of motion comes from the principle of extremal of action.
Yeah.
Now you are saying this extremizing this does not give you the equation of motion.
By following the traditional calculation.
Tradition. If is the extremum of this the equation of motion or not? For dissipative system?
No.
Then what is the point of making this action?
The point of making this action is like taking a different approach by this. What different approach is that? If we took this Lagrangian.
So this extremizing this does not give you the equation of motion.
Exactly.
And why do I even expect it to be minimum for the actual path? If it I mean, so you're saying that let me take N to be that, right? Now for ED I substitute this into Now if I try to extremize this, I will not get the correct equation of motion. हो गया mathematically. उसको simulate करने की क्या जरूरत है?
They have taken used the different mathematics to get the correct result by taking this Lagrangian. Basically,
no, but this Lagrangian does it extremize taking this Lagrangian?
Yeah.
Does extremizing this S by hand mathematically does it gives you the wrong equation?
Yeah, it gives.
But you use the correct equation to solve for the correct equation to check if for the correct path this is the minimum or not, right? No. What that plot date that you had? What equation have you solved to calculate S?
Basically, sir, what is the basically result they have given? Basically, let's suppose I am explaining.
So forget that. What have you done?
What I have actually done, I have simulated the action by using his approach. What he has taken.
But the action calculate तो किया होगा ना?
Yeah, by using this.
कोई trajectory calculate किया
Yeah.
होगा? वो trajectory कौन सी equation solve करके calculate?
Basically, the action is calculated by using this equation.
अरे भाई equation तो ठीक है, L कैसे निकाला?
L is following.
ये मगर उसके लिए तुम्हें हर point पे position और time चाहिए होगा, वो कहाँ से निकाला?
Basically, let's suppose like
कौन सी equation solve करके निकाला?
let's suppose we take an equation like a particle is moving from here to here. We have a true trajectory.
अरे वो trajectory निकाली कैसे?
By using the equation of motion.
कौन सी equation of motion? गलत है ठीक?
सही equation of motion.
सही equation of motion ठीक करके तुम check करो सही equation of motion के लिए S minimum नहीं है तुम ये कहना चाहते हो?
No sir.
हाँ तो क्या कहना चाहते हो?
Give me 1 minute please. Basically, what is happening here?
पीछे जाओ पहले slide पे जाओ.
Please give me 1 minute sir.
हाँ कोई जल्दी नहीं. वहाँ दिखाओ जहाँ disagreement है वो मुझे दिखाओ. agreement हाँ ये लास्ट वाला दिखाओ. ये ऊपर वाले दिखाना तो इसमें एक red line. Red line is action for what?
Red line is the action for the true path.
What is the true path according to you?
the true path according to me is the path that is obtained by using solving the equation of motion
और
of
इक्वेशन
further.
मतलब करेक्ट इक्वेशन होना
Exactly.
ठीक है
But-
उसके लिए तुमने एक्शन निकाला
Yeah.
मगर वर्सेस पाथ कैसे कैलकुलेट कर रहे हो
ये
एक्शन
बात-
वर्सेस पाथ का क्या मतलब है
Action versus path means basically we have taken the perturbation around 100 paths and we have calculated the action for each perturbated path and we have plotted the action with the path and let wants to see.
नहीं वो चलो
Yeah.
ठीक लाल वाले तुम एक्शन की वैल्यू कह रहे हो ट्रू पाथ के लिए
Yeah.
सॉल्विंग द ट्रू इक्वेशन ऑफ मोशन
Yeah.
और तुम यहाँ शो कर रहे हो कि जो पर्टर्बेशन है उस पाथ के लिए कई बार एक्शन कम भी हो जाता है
Yeah.
वो सरप्राइजिंग क्यों है क्योंकि ये एक्शन जब असली इक्वेशन ऑफ मोशन से एक्सट्रीमाइज होता ही नहीं है तो मेरी चेक करने की क्या जरूरत है मैं ये नहीं कह रहा तुमने गलत किया मैं तुम्हें कह रहा हूँ मुझे समझ नहीं आया
Okay. Let me explain. Basically, what you were saying that I am getting with the best one. Yeah. Basically, let's suppose you get a equation of the true path. UT plus R. Let's suppose it's a parabolic path. This is the true path that can be obtained by using equation of motion or Euler-Lagrange equation. Now, you want to calculate the action for this path by using this equation, by using even this Lagrange. Okay.
वो कहाँ से आ गई इसमें तो ईडी है ही नहीं इस इक्वेशन में
इसके लिए let's add some factor theta p. Theta is a dissipating constant. Okay. Then add some factor. Now you can calculate the action by using this. Okay. And you know the value of action. Now you want to see or look. Let's suppose there is a lot of path that can be possible between 2 points. Now you want. Let's suppose I have taken 100 different paths. How can I take this? I can take this by using polynomial.
वो छोड़ दो
Yeah, yes, sir.
उसको छोड़ दो
Let's suppose I have taken 3 different paths. That is x1 key. For which there is epsilon factor, some adding factor.
ठीक है
X2, let's suppose the other path. Now I have calculated for this path the value of action.
और तो कम आ गई ऊपर वाले से
Let's see what
नहीं
happens.
बात
Not always.
नहीं कभी कभी कम भी
हाँ,
आ गई,
कभी-कभी कम।
कभी ज्यादा भी आ गई।
कभी ज़्यादा भी आगे.
फिर
और फिर
व्हाट इज द पॉइंट क्योंकि क्योंकि ये जो इक्वेशन तुमने निकाली
Yeah.
वो उस एक्शन को एक्सट्रीमाइज करके आती ही नहीं है
which means using this Lagrange.
ये लैग्रांजियन से जो एक्शन निकाला
हाँ।
उसको एक्सट्रीमाइज करके तुम्हारी x ऑफ t वाली इक्वेशन आती ही नहीं है
Euler Lagrange equation आती है सर.
भाई असली इक्वेशन ऑफ मोशन आती है कि नहीं आती
आती है सर.
तुमने बोला नहीं आती
Problem is nothing in between the mathematics. We can use different mathematics, sir.
एक मिनट अभी तेरे को मैं कंफ्यूज हूं या मेरे को तेरे को समझ आ रही है चक्कर
I'm also a bit. So, are you trying to say if you are using that particular action, you are kind of minimizing the action, then traditional way that
Exactly. The problem is occurring in the traditional mathematics.
So where is that step? What is exactly happening over there? Why is it?
The problem is coming in the step of solving the double integration. In the case of double integration, they are acting a known locality and you are getting a wrong equation. So what he has done, he has used different mathematics by taking the same Lagrange, but using different mathematics or some different conditions and arrive to the correct equation. Now my work is to check.
नहीं वो ठीक है मगर वो इक्वेशन किसको एक्सट्रीमाइज करके तो नहीं आती
No.
तो फिर उसकी जो सॉल्यूशन है
Yeah.
वो उससे ये मिनिमम आएगा ही क्यों
I get your point. What you are saying basically, you are saying that if you are unable to get the correct equation by using this expression, then why again you are using this expression for calculating the action?
No, you can use the expression to calculate the action, but it will not be minimum. Why do you expect it to? तो मतलब what is new, what is surprising about that red line कि नीचे भी blue है ऊपर भी blue, surprising क्यों?
The surprising thing is that as the paper was done by Van, he plotted everything. Okay.
ये किसके ने प्लॉट निकाले हैं?
This is for spring mass, like that I have.
ये
done.
स्प्लिट
This is mine.
हाँ
This is his. He has plotted. My work is to check his theoretical idea whether what he has done is correct or not.
मगर उसका theoretical idea तो ये है ही नहीं कि S minimum होना चाहिए। बस जितना मुझे समझ आया
Yes, sir.
तो हाँ जितना तुमने मुझे समझाया उसके हिसाब से तो मुझे लग रहा है कि उसका आइडिया है ही नहीं कि S minimum को तो क्लेम ही नहीं कर रहा।
He has. Maybe you are not getting what I am saying. Maybe I could not be able to make you understand what actually I want to say to you.
तुम
Basically.
दोनों बताओ मुझे मैं कंफ्यूज हूँ। नहीं आई एम honestly, I'm asking you very honestly.
Yeah.
So this is interesting. This is interesting. This is a nice dynamical system approach. Go ahead. What is going on? What am I missing?
I get your question and you're going back and forth.
So all I'm understanding is why is it a surprise
Yes, sir.
that for your system it is not a minimum. I'm surprised that for him it is. In fact, how many actions, how many paths has he checked? Infinite number of paths that he can.
He has taken only 100 paths.
तो what if 1000 लेता तो उसका भी तो हमारे
हाँ,
जैसा
different
आया
आता है। The
तो
situation
हमारे जैसा आ जाता है
different होगा।
Can you move it a little bit to see the
अब अच्छा ये इस अगर उसने 100 पास के लिए ये चेक किया कि मेरा एक्शन सबसे कम है इनमें
For a certain case.
हाँ हाँ वो सब पेंडुलम के लिए
No, for pendulum, even for certain parameter.
नहीं पेंडुलम के साथ कुछ और, ये सिर्फ पेंडुलम है।
Pendulum भी है, but changing. I'm saying.
पेंडुलम की इक्वेशन क्या दी है?
Yeah, let's see. This is the equation. Let's see. This is the equation of a spring.
नहीं तो उसकी बात
This
बताओ।
is yours.
उसी कौन सी इक्वेशन है पेंडुलम पर?
You can change here by theta.
लिखो वहाँ इक्वेशन पेंडुलम की इक्वेशन उसमें कौन सी ली है? अच्छा उसमें ये ली है।
Yeah. He has calculated his solution. Theta as a function of t. Then using polynomial approximation, he has calculated 100 perturbated path. And by using that action, he has calculated action for every path, every perturbated path, including the like two path equation. That is
उसने
basically.
राइट हैंड साइड ली थी नहीं ली थी?
Yeah, this is the point, sir. He has only taken the damped force, not force. Damped oscillation. I have taken damped plus force, and now verifying his idea.
बट उसमें मिनिमाइज एक्सपेक्ट ही क्यों कर रहे हो कि वो मिनिमम होगा?
It takes time to explain. It actually takes time.
कोई बात नहीं, ओके फाइन।
Yeah,
We will discuss later.
yeah, I will definitely discuss with you. What the concept of the point. Is there any question?
So can you explain to me all this and just say like a
layman language.
no not layman. Say that you have a one-dimensional system
Yeah.
and you have a conservative force
Okay.
and say you have a frictional force.
Okay.
F. How will your Lagrange equation look like?
Yeah, exactly. If I
Just write it down.
okay. Basically, what he was saying.
So this friction force and
There is,
conservative force.
there is a body which is falling down. Simple example, free fall.
Okay.
This is happening in the environment of friction. As you know, here the drag force of friction is like proportional to velocity. You can take minus
So
g.
just say it is at F.
Velocity to the power 1. I have taken 1 and 3 2. Okay. For the linearly damped and cubic damped. So here you can you can know the force like force of gravity and the force of damped friction that is acting over here. Now after that, if you want to write the Lagrangian here, the Lagrangian will be K equals to kinetic energy of this body that can be written as a half m y dot square minus potential energy changing of the body. If you take the reference as a like
Leave the Lagrange, what is the final equation? Final equation of motion.
final equation of motion.
Write it in terms of the partial derivatives of the Lagrange.
You can take from here. Put the v equals to minus of m dy. It will come to mx double dot minus or every thereafter you can put minus v to the power 1. V you can write as a y dot power 1. Your equation will become like this. Then you write mx double dot minus mdy plus v to the power 1. Here in the case of 1, in the position of 1 I have taken 1 and
I get that. I was asking this in terms of Lagrangian writing.
I'm writing
So that's just in terms of. Never mind. It's just generalized force and moment.
this is the this is the kinetic
Just
energy.
write as partial L del L by del X. Just write.
Right, Lagrange's equation.
Lagrange's.
Euler Lagrange equation. Okay, you are talking about Euler Lagrange equation. Sorry. The general Euler Lagrange equation is like that.
What if there is a friction? How will you get it?
Here the friction term can be aided by using this. This is the amount of energy distributed to the environment that can be calculated cross introducing method in moment, where ED can be calculated in this manner. This, as you can see, x1 to x2, f d x dot, which is the function of position and velocity, and dx can be written as a x dot t. So from here you can calculate the ED terms. Thereafter you can put the ED terms over here, and you get the Euler-Lagrange equation in the form of dissipating system. So by there you can calculate the action total.
So if we have a system and an environment, with the potential energy only, what will the potential energy
It will be like there is also a plot of potential energy, kinetic energy, and dissipative energy.
Is it only depend on position?
No, basically we are taking depends on position, and in the case of electromagnetism, there is a potential that is depending on the velocity. That system is also a non-conservative system. But in our case, we are taking basically.
What about time?
Huh?
Will the potential depend on time?
No, not in our case, but it can depend on time. It can depend on time. But in our case, we have not taken the position to depend on time. We basically took the case. Potential to depend on only position, basically. And so I definitely give you the answer because this is my dissertation. What I want actually your suggestion. What I am actually doing wrong here.
If you have a charged particle moving in a magnetic field, is its energy conserved or not?
If a charged particle, no sir. Because if charged particle is accelerating, it is
No, forget it. Ignore radiation. If you ignore radiation,
then
is its energy conserved in a magnetic field?
yes sir, then it will be conserved. Like if it is not radiating energy or like emission, then the energy will be conserved.
What is the expression for its conserved energy in terms of a magnetic field?
In terms of magnetic field, you can write currently not really right.
But why do you say the Lagrangian for a charged particle is dissipating? Why did you say that?
Basically, I am saying that in the case of accelerating charge particle, the system is non-conservative. Accelerating charge particle is a non-conservative system.
It is an accelerated charge particle, you cannot even write a Lagrangian for it.
Yeah, exactly.
So we start by plotting the Hubble parameter, and we assume that all parameter values are independent and they are all normally distributed. Over here, essentially what happens is that we are trying to find the likelihood of a certain value of omega m to fit into this model. So we have a certain data, we generate data, a bunch of random variables of omega m ranging from 0 to 1, and we put that data into this given model to see where the likelihood of that data existing is maximum. And this is essentially the Lambda-Sabin model, the equation we use to find out which value of omega m fits best into this model. From here, we were able to find the most, at least chi-square value. We were able to find, we will discuss the formulation later, but at the least chi-square value, we were able to find omega m's value to be 0.29 and omega lambda to be 1 minus 0.29. Then we move on to comparing the Newtonian and Gawa profiles of our given data set of galaxy clusters, which consisted of the masses of those galaxy clusters at varying radial distances. We use the following formulations for acceleration at Newtonian profiles and acceleration at the Gawa profiles, and we were able to compute lists comparing the fractional difference.
Important mission of NASA failed due to ignorance of this effect. So yeah, that's all I want to say.
The speaker spoke for 12 minutes and 15 seconds.
You first year? Good, excellent. So, you've studied rigid body rotation, obviously.
Yes, sir, the first semester.
Okay. So, is angular velocity a vector?
So actually, it's a very confusing concept related to angular velocity.
Is angular velocity a vector or not?
So if I take in with for reference, like I studied a derivation of the I already said Euler's laws of motion. It consists. Can I draw it?
Euler's equation.
Not sir, not the equation, just the diagram. Let's suppose this is an inertial frame, okay? And we are taking a rigid body over here. These are the principal axes, x, y, and z. And this is the point about which it is rotating. Okay, it has some omega. Omega, but with respect to this.
But omega is, you've written the vector omega, right? It
Yes, sir.
exists.
Yes, sir, it is the product of R cross V. It is very confusing because, like mathematically, if we go for the vector product, R cross V, cross product always gives us a vector. But when,
Omega is R cross V.
sorry, I feel virgin actually.
What is?
So for this situation, I consider omega as a vector.
Okay, omega is a vector. Is angular momentum a vector?
Yes, sir.
Okay. What is the relationship between angular momentum vector and omega vector? Can you write down the mathematical relationship?
So say, since any angular quantity is the movement of that linear quantity, so we can begin with this.
No, this is just a particle. This R cross V is only for one particle. This is a rigid body. The rigid body has some angular momentum.
Okay, okay, sir.
It has some angular velocity. What is the relationship between the angular velocity and? So just write it in a box. A equals I omega. Is this true?
Sir, we studied the derivations using Newton laws and also Euler's motion.
So this equation is true. So you calling it M. Here,
Yes,
right?
sir.
So that is M, right? So write M equals I omega, right? That's M. That you
Yes.
write. Is this true? So now
Yes, sir.
resolve this. Mx would be I omega x, and y would be I omega y.
So actually, one thing my teacher told in the school that I already told. Any angular quantity is the movement of any linear, same linear quantity. So if we talk about angular momentum, it is if we take into account the linear momentum. Linear momentum is the product of m, mass, and velocity. Here in rotational motion, we have I as mass and omega as
That's
velocity.
fine. So this equation is correct. You claiming? Let's go back to your slides.
So which one?
Let's see. Slowly. Back. Wait. Okay, back. अभी n square I1 square अब यहाँ तो एक ही I है वो तीन I कैसे आ गए यहाँ पर? In this equation, if you've written n is I omega, यहाँ देखो you've written n is I omega. Which of these I's is this? यहाँ नीचे देखो ये
अच्छा
model
सर,
ये I1 है I2 है I3 कौन है उनका square root I1 square plus I2 square plus I3 square क्या है? How is this I related to I1 I2 I?
Sir, see, I1, I2, and I3 are three possibilities to which a body can rotate.
But here
Here we take in account the rotation about which it is happening.
so is this equation correct or not correct?
Yes, sir, to dimensional analysis and by comparison.
Okay, who guided you on this project? No one? You read a paper by somebody?
Sir, paper, videos, and books. Of course, we have mechanics and little reference.
So what excited you about? How did you bump into this
Sir,
problem?
actually one day randomly my friend sent this video and I was like, okay, nice sir, this looks good. But then I just started noticing that these things happen in space also and here also. One thing is that I aspired to be a space scientist maybe a few years later. So during the space mission, as I already told, one NASA mission, I don't remember the name, it failed due to the ignorance of the flaps that it was having.
What was happening?
The structure of the that rocket was like this and it had flaps.
Oh.
So these flaps actually caused the Zelenov effect and this mission failed.
Oh.
So that's why I want to bring in this notice so that all future missions they actually.
It's fine. But have you understood where all these expressions are coming from? E equals half I1 omega 1 square I2 x square. And you just, since you know some mechanics, don't you think you should maybe derive these or try to understand what these are?
Yes sir, yes sir.
How these come from?
Yes sir, as I read the research paper, it mentioned that there are 3-4 ways. And one was a Laplace multiplier and the other were quantity.
It's extremely simple. This
Observe.
this equation is very simple to derive. You don't need Laplace or anything complicated. You just need to know the expression for angular momentum of a rigid body.
Yes, sir, I get it. For energy of a rotational object, if it is just under the rotation, it is half I omega square. That we all know since class 11.
Yeah, half I omega square. These terms are like
Yes, because we have E is equals to half I omega square. But since it is a vector, and either we will take into the we will take account of the magnitude, or we can simply do this. This also gives us the omega square. But omega, since as I took omega as vector, omega xi plus omega yj plus omega zk, the three components. So if we take in the magnitude, this gives omega vector if it is a square. So this gives omega x square plus omega y square plus omega z square. And one thing I already noticed, I told that here it is wrong. That this will not be this will not be 2 or 3 because it is rotating about a single axis at a single point. So it will be either that will be taken in common, and then this omega square will be written in a place. And when we will take I1 inside the bracket, we will get this kind of expression.
Can you go back to the slide where you showed the picture of the big D? Yeah. Yes. Yeah. There is no external force. Does that imply there is no force?
Yes, sir, because torque is the movement of force itself. So if we take that force, external force, net external force on a body is 0, we can say that torque external is 0, and then we will take angular momentum.
Are you sure that if the net external force on the rigid body is 0, the net torque is also 0? Social school class में पढ़ा
Take a pencil.
No, they just make a disc. So the example पढ़ा हुआ class.
Okay, sir, I got it. That you are saying this is a pencil and we have the force in opposite directions. There will be a torque, but the net force will be 0.
So how did you claim that? How did F external equal to 0 imply tau external is 0?
So actually I talked about an object in a free space. And considering in the free space, we know that there is since it is in space shuttle, the weightlessness is there due to the normal force balancing and gravity balancing.
Normal force? Which normal force?
No, sir.
This is moving inside. There is no normal force.
Yes, sir. What I meant is there is weightlessness inside. There is no gravity inside that space
There is
shuttle.
no gravity
There is
there.
no gravity.
So
No,
there is-
wait. In a spaceship, is there gravity or not? Okay, so let's say there is a satellite in orbit around here, right? उसमें भी ऐसे ही होगा ना, one person who discovered this, must be satellite in orbit around the Earth. So inside that satellite, does Earth's gravity effect, is its effect there inside the satellite or is it not?
So it is not actually. It is balanced by some other forces.
What other forces are there?
I'm really
So let's say this astronaut really saw it spinning in space. Let's look at this. It is acted on by the Earth. What other forces there to balance it? Or is it not or is there gravity in space or not due to the Earth? Is there gravity?
Yes, sir.
Is there?
Gravity is there, but we need some other force to balance it.
Where is that other force?
Is not able to recall it right now. Thank you.
Logic is important since F50 is something that is usually used in signal processing. Our case stands as a novel case where F50 has been used in the physical sciences. Now I move on to the actual computational part of our project. So the very foundational case we have considered is the monatomic linear chain. Now in the case of a monatomic linear chain, essentially it consists of identical atoms with identical spacings between them. The dispersion relation that we expect for a monatomic chain, as is evident in figure 2.1, mirrors that of a low pass filter, which is to say that the nominal frequencies that exist within a system cannot be higher than 2 root over alpha by n, which is the normal frequency of the Brillouin zone modulator. Moving on, now when we computationally modeled it, the way we did it was essentially we link two atoms to the atoms are identical, they have identical masses by elastic strings of the same force constant alpha in a cyclical manner. Of note, only nearest neighbors are taken into account. Now here we move on to the results portion of the presentation. So we have the monatomic linear chain, and I've given it some parameters. And the theoretical value, as can be seen, is it's 1.0, and the F50 computed value is also 1.0. So we can see it's in agreement. Moving on, I've changed the parameters to see whether it exhibits the accuracy for other parameters, and it does, as can be seen on the board. It does lose an accuracy at the 0.001 level, but in general it is in agreement with its results, with the theoretical results. Now, summarizing what I've discussed so far in the monatomic case, we have, as was evident, the F50 is able to capture the behavior of the phonons at the Boulogne zone boundary, and this is irrespective of the initial energies of the atoms. And this is something I'll come back to later regarding the initial energies. As can be seen, the accuracy was over 99.9%. Now, I move on to a slightly more complicated case of the of a lattice structure, and that is the diatomic linear chain with the basis. Now, the diatomic linear chain with the basis, essentially, it consists of dissimilar atoms spaced with dissimilar spacings. So, as is visible in figure 3.1, so we have two kinds of atoms. We have the atoms with capital mass M and atoms with lowercase mass m. Now, since the spacings are different, we have two different kind of elastic springs in use, that is alpha and beta. And since the length of the beta stands for the cases where the spacing is larger as compared to alpha. Now, when we construct a unit cell for this case, as is visible in 3.1c, we have two pairs of alternating dissimilar atoms. 3.1b showcases the dispersion relation we expect, but of note here is that we have an optical branch and an acoustic branch. Now, an optical branch is essentially when the neighboring atoms have a phase relationship of pi, while an acoustic branch have a phase relationship of 0, the neighboring atoms. Now, let's move on to the computational model, and figure 3.2 is a direct follow-up to figure 3.1c, which is essentially we connect this beta spring in a cyclical manner to the beta spring on the other end, and we end up with this. And this essentially, the unit cell we have constructed for our case consists of 3 lattice sites, which while modeling 4 atoms. Now, why 3 lattice sites? So, if you see, when we our unit cell essentially, if we repeat it, then we get an infinite lattice. So the outer 2 atoms are shared with other unit cells. So they have a contribution of half, while the interior ones are only contained within the unit cell. So they have a contribution of 1 each. So you have 3 lattice sites. Now the 3 lattice sites lead us to expect 3 normal frequencies, and the frequencies we're looking out for, represented by the angular frequency form, are omega 1, omega 2, and omega 3. For your reference, the formula is there. Now, when we plug in our values for alpha, beta, and small m and capital M, the theoretical values we expect, as given on the board, are those, while the F50 values are within 2% error, and this error can be attributed to a slightly more complex system being studied here. But still, as can be stated here, that the F50 computed values are still in agreement with the theoretical values. Moving on, I have a special case with the within the diatomic linear chain, where we still have dissimilar atoms, but the spacing is equivalent. In this case, so essentially compared to our diatomic chain with the basis, this is a case where alpha becomes equal to beta. Now we still expect the same phonon frequencies, omega 1, omega 2, omega 3, but here alpha is equal to beta. And accordingly, when we get an F50 plot, of interest here is that in all the cases I've shown you so far, all the particles, all the atoms will display the same phonon frequencies. However, in the case of the diatomic linear chain with basis, the atoms display 2 different normal frequencies. Moving on, on to the most complex case we've studied is the monoatomic spell lattice. So this is a 2D structure and our atom have 2 degrees of freedom. We have had to account for these 2 degrees of freedom by taking into account both the nearest neighbors and the next nearest neighbor interactions. And we have also taken into account the angular forces, represented by angular force masses beta 1 and beta 2. So the angular force mass is essentially the restoring force on an atom due to another atom whose displacements are perpendicular to the line joining the 2 atoms. I'll move on to the computational model. So our computational model essentially consists of 9 atoms. We have a larger error here of around 5%, but it still contains the 4 phonon frequencies expected, and they are well in agreement. Now, summarizing up my presentation, as I have displayed to you, the phonon frequencies are indeed captured by the FFT method, and as I had said in, I believe, to slide 2.1, the phonons, the phonon frequencies are not dependent upon the initial energies of the atoms, that is the initial displacement we give to them. And with that, I come to the end of my presentation. Thank you. I'm open to questions.
The speaker spoke for 12 minutes and 16 seconds.
Okay, so what you've done is you've made a simulation, a few atoms using which algorithm? RK4.
Yes, we have solid equations of motion in the using RK4.
RK4. And what kind of initial conditions did you use?
In initial conditions, essentially the initial energies we give to the atoms, that has been implemented using it has been randomized. So since essentially our case is what it's like if you think of it in the Newtonian sense, it's particles attached to each other by strings, and we solve this using RP4.
No, that I know. But in the algorithm, you have to give initial conditions. What kind of initial conditions did you give?
The initial conditions are essentially you have the initial conditions have been given using like a random, like the initial values are random in nature.
What initial conditions do you have to give? Just explain to me what way.
I understand the question now. So the only initial conditions we have to give are the initial displacement of the atom. So I guess I'll draw. Okay, this part. Is there a dust?
Just give for the simplest example that you can.
Yeah.
The simplest example, you had only 2 atoms.
Yeah.
What do you, when you solve the differential equation, just explain to me what giving an initial condition means.
Yes. So we have our the monoatomic model. So let's say this is my equilibrium site. So I have the mean displacements x1 and x2. Now the equations of motion, both are m. Since this one attributes to the
That's fine. Yeah. So fine.
So the in our RT4 method, so it's essentially what we solve it for our initial conditions.
So what do you mean by initial condition?
Okay, the initial conditions. So so this is a differential equation. So let me just represent any differential equation. X dot. Okay. So when we use RT4 method, we have we represent x dot as a, and so our initial we need to have an initial condition for the parameter x